Bitcoin has emerged as a leading digital currency, captivating global attention since its inception. This revolutionary form of money has not only intrigued tech enthusiasts but also caught the eye of investors, economists, and governments worldwide. Its rise has sparked debates, discussions, and even regulatory actions, as traditional financial systems grapple with the implications of this new digital asset. Operating on a decentralized network, Bitcoin is free from the control of governments and financial institutions. This decentralization is achieved through a technology known as blockchain, which ensures transparency and security by recording all transactions on a public ledger. The blockchain is maintained by a network of computers known as nodes that work together to validate and record each transaction. This decentralized nature of Bitcoin allows for peer-to-peer transactions, enabling users to send and receive value directly without intermediaries. This means that transactions can be faster and cheaper compared to traditional banking systems, which often involve multiple steps and fees. For many, this represents a significant shift in how we think about and use money. Imagine a world where you can transfer money across borders as easily as sending an email. This is the promise of Bitcoin, offering a glimpse into a future where financial transactions are seamless, borderless, and instantaneous. This potential has led to a growing acceptance of Bitcoin in various sectors, from online retailers to service providers, and even charitable organizations. The promise of Bitcoin extends beyond just ease of transactions. It also offers a level of financial inclusion for those who are unbanked or underbanked, providing access to financial services for millions of people around the world who are currently excluded from the traditional banking system. This digital currency relies on a secure system called cryptography to protect transactions and ensure their authenticity. Cryptography involves complex mathematical algorithms that secure the data, making it nearly impossible for unauthorized parties to alter or forge transactions. This security is one of the key reasons why Bitcoin has gained trust and popularity among its users. However, the emergence of quantum computing presents both challenges and opportunities for Bitcoin and the future of digital currencies. Quantum computers have the potential to break the cryptographic codes that secure Bitcoin transactions, posing a significant threat to its security. On the other hand, advancements in quantum computing could also lead to new, more secure cryptographic methods that could further enhance the security of digital currencies. Understanding this complex interplay between current cryptographic methods and emerging quantum technologies is crucial for navigating the future of finance and technology. As we move forward, the ability to adapt and innovate will determine the success and resilience of digital currencies like Bitcoin in an ever-evolving technological landscape. The digital revolution brought about by Bitcoin is just the beginning. As technology continues to advance, the ways in which we interact with money and conduct financial transactions will continue to evolve, shaping the future of our global economy. At the heart of Bitcoin's security lies cryptography, the practice of secure communication in the presence of adversaries. Bitcoin utilizes a specific type of cryptography known as public key cryptography or asymmetric cryptography. Imagine two keys, one public and one private. Anyone can send you a message using your public key, but only you can unlock it with your corresponding private key. Bitcoin transactions rely on this system. When you send Bitcoin, you use your private key to sign the transaction, verifying your ownership. The network then uses your public key to confirm the transaction's authenticity. This intricate dance of keys ensures secure and trustworthy transactions within the Bitcoin network. Quantum computing, a paradigm shift in computing power, harnesses the principles of quantum mechanics to solve complex problems that are intractable for classical computers. Unlike traditional computers that store information as bits, zeros and ones, quantum computers utilize qubits. Imagine a coin that can be both heads and tails simultaneously. That's the power of a qubit. This unique property, known as superposition, allows quantum computers to perform computations at an exponentially faster rate than classical computers. This groundbreaking technology holds immense potential for advancements in fields like medicine, materials science, and artificial intelligence. However, the same power that promises progress also poses a potential threat to the cryptographic foundations of Bitcoin. Section 4. Quantum Threat: Breaking the Encryption Code. While quantum computing offers exciting possibilities, It also presents a potential threat to Bitcoin's security, specifically to the cryptographic algorithms that underpin its infrastructure. Quantum computers operate on principles fundamentally different from classical computers, leveraging the strange and fascinating properties of quantum mechanics. This allows them to perform certain calculations at speeds unimaginable with today's technology. The security of Bitcoin relies on the fact that classical computers would take an impractically long time to break the mathematical problems protecting its keys. These problems are designed to be computationally infeasible for classical systems, ensuring that the encryption remains robust against traditional hacking attempts. However, the advent of quantum computing changes this dynamic significantly. However, quantum computers excel at solving specific types of mathematical problems, some of which form the basis of Bitcoin's security. For instance, they can efficiently solve problems related to factoring large numbers and computing discrete logarithms, both of which are integral to the cryptographic algorithms used in Bitcoin. This potential vulnerability arises from the fact that quantum computers could, theoretically, break the encryption codes that protect Bitcoin wallets and transactions. If a sufficiently powerful quantum computer were to be developed, it could decrypt the private keys that secure Bitcoin addresses, leading to unauthorized access and potential theft of funds. This risk, while not immediate, necessitates proactive measures to ensure the long-term security of the Bitcoin network. Researchers and developers are already exploring quantum-resistant cryptographic algorithms to safeguard against this future threat. By staying ahead of the curve, the Bitcoin community aims to maintain the integrity and security of the network, even in the face of advancing quantum technology. Section 5. Shor's algorithm. The Bitcoin breaker. One particular algorithm, known as Shor's algorithm, poses a significant threat to Bitcoin's cryptography. This algorithm, if harnessed by quantum computers, could revolutionize the way we understand digital security and encryption. Developed by mathematician Peter Shor in the mid-1990s, this algorithm demonstrates the ability of quantum computers to efficiently factor large numbers, a task considered computationally infeasible for classical computers. Shor's work was groundbreaking, opening up new possibilities in the field of quantum computing and cryptography. Imagine trying to find the prime factors of a massive number with thousands of digits. This is a problem that classical computers struggle with, as the time required to solve it grows exponentially with the size of the number. For classical computers, this task would take billions of years. The sheer computational power required is beyond the reach of even the most advanced classical systems we have today. Shor's algorithm, however, could theoretically accomplish this feat in a matter of hours on a sufficiently powerful quantum computer. This is because quantum computers operate on principles that allow them to process information in fundamentally different ways compared to classical computers. This ability to factor large numbers directly undermines the elliptic curve digital signature algorithm, or ECDSA, which forms the foundation of Bitcoin's security. ECDSA relies on the difficulty of factoring large numbers to ensure the security of transactions. If successfully implemented on a large scale, Shor's algorithm could potentially compromise the integrity of Bitcoin's public key cryptography. This would have profound implications not just for Bitcoin, but for the entire field of digital security, as many systems rely on similar cryptographic principles. The advent of quantum computing thus presents both a challenge and an opportunity, pushing us to rethink and innovate in the realm of cybersecurity. Section 6. Post-quantum cryptography, building a stronger shield. Fortunately, the cryptography community is not standing still. Researchers are actively developing and implementing post-quantum cryptography, or PQC, a new generation of cryptographic algorithms designed to resist attacks from both classical and quantum computers. These new algorithms are like building a fortress with stronger materials and innovative designs. They are built upon mathematical problems that are believed to be difficult for even quantum computers to solve, providing a robust defense against future threats. PQC research encompasses various approaches, including lattice-based cryptography, code-based cryptography, and multivariate cryptography. These advancements aim to ensure that Bitcoin and other cryptographic systems remain secure, even in the presence of powerful quantum computers.